So we're going to talk about tropical storm and Hurricane Melissa today, and tropical weather in general. So we're going to start just looking at Melissa. I want you to notice all the convection popping up down here in this area. Here's Jamaica way over here. At this point in time, we just have a tropical depression. You have no well-defined low pressure system. Notice here, the spin has begun and how it winds up really tight there. That's when it became a hurricane. At that point, it was a Category 4 hurricane. You'll notice it keeps drifting to the west. You can see a clearly defined eye, but notice all the bands around it too. And when it went across there, it had almost an absolutely perfect picture of a classic hurricane. Here it weakened and gradually dissipates. So this is what we're going to deal with today. I want to talk a little bit on how hurricanes form, what the difference is between the tropics and where we live in the mid-latitudes. So we'll go with tropical weather systems. So what conditions are required for the tropical cyclones? We know, for example, that Hurricane Katrina was one of the most devastating hurricanes ever in the United States. It occurred back in 2005. It hit the Louisiana, Mississippi Gulf Coast, claimed over 1,200 lives. So it proves just how destructive hurricanes, these tropical systems, are to the weather. And Hurricane Rita followed less than a month later and actually overflowed a lot of the same area. So where is tropics? Tropics exist wherever the sun can be directly overhead. Now, the directly overhead means it goes between 23.5 degrees north and 23.5 degrees south. So almost no cold fronts, no warm fronts reach this area. All that we talked about, the extratropical side of weather, last week, don't reach here. So this air mass is uniformly warm. Much of it's very humid. Some of it's quite dry over deserts, but all of it hardly ever changes temperature. The seasonal change in temperature is far less than the daily change in temperature. So in other words, the difference between the high and the low that day is more than would occur between winter and summer. There are thunderstorms in the tropics. Many of them occur around the intertropical convergence zone where we know winds come together. And that moves with the sun. So in our summertime, it is pushed way up to the north. In our wintertime, it's pushed down south. Now, how do we analyze things in the tropics? We've always done our analysis by isobars or contours, looking at pressures. Pressure doesn't change much. There's hardly any pressure gradient except within tropical cyclones. So with that being the case, we need some way to do an analysis. What we do is literally take the winds and draw a line literally following the wind. So in other words, if a wind's moving from the east, we'll follow that line. If the wind turns to the southwest, maybe we'll follow that line. That will be our analysis. We'll see streamlines. So hurricanes are a very intense cyclone, very different. Extratropical cyclones are very large, have a extreme temperature contrast, and get stronger with height. We learned all this past week. Now this week, hurricanes are warm core, so they actually warm as you go to the middle of the storm. There's no circulation of temperature difference around them. They're very little. It's all humid. We saw dry air masses moving in on the west side of extratropical storms. That doesn't occur with a hurricane. And they weaken with height. We learned that as you go up with height in a very warm air mass, the pressure doesn't increase as fast. So you wind up with higher height. Well, you actually have, in many times, high pressure over top of a hurricane. So here's an eye of a hurricane, and here's what they call the cathedral effect in a hurricane's eye, where the plane looks in there and just sees a tremendously intense area of thunderstorms around the eye wall. So if you were in the eye of a hurricane, you would have almost no wind, pretty nice weather actually, However, and it would be quite warm and very humid. However, once the eye left, winds would immediately increase to the highest they're going to be. So the change from one side to the eye to the other is extreme. Eye walls are definitely the most dangerous part of the storm. And the direction the storm is moving on the right side where the wind is coming from typically, that direction adds a little bit of speed to the wind, so the winds be slightly stronger in that area compared to other areas. And here is an actual image looking at how the bands around the hurricane. I showed you that with Melissa. There were several bands, especially on the east side. They don't always wrap around smoothly, but the eye wall in this area, almost all the bands are right there, wrapped into together. You look at the eye and you expect to see a perfectly cylindrical in the most intense hurricanes, like Melissa was. Weaker ones won't be as good. And notice the air comes up and out, so you would get great divergence at the top of the eye. So that allows the air to be pulled upwards all around it. And in the middle of the eye, there's sinking motion. There are certain conditions necessary for tropical cyclones. One of them is high sea surface temperatures. Matter of fact, sea surface water temperatures must be greater than 80 degrees to at least 150-foot depth in the ocean. Otherwise, we're not going to be able to sustain a hurricane. There also needs to be a Coriolis effect. You don't get hurricanes at the equator. Weird, I know, but you must have something that turns the wind so that it can create a low pressure system. And where we wanted strong wind shear to develop the thunderstorms we just talked about, well, now we want no wind shear. We want very light winds aloft initially so that the thunderstorms will go straight up and continuing to be built in this very tropical humid air mass. Finally, we need the whole air mass to be humid. In other words, if there's dry air that gets mixed in, it's going to weaken these hurricanes. So where do you look for these warm spots? Well, I wanted to show you here one of the warmest areas in the eastern hemisphere, in the western hemisphere, excuse me, is right here just south of Jamaica. So where Melissa formed actually had some of the warmest water all around. So that is why it gained its strength. It had such tremendous warm water. We also have tremendous warm water sometimes in the Gulf of Mexico. And along the Atlantic coast, when the storms move right over the Gulf Stream, there's some very warm water. So typically on average, each year, there's about 85 tropical cyclones globally. Globally means Western Pacific actually has the most, and that is areas like the Philippines, Japan. That area has the most tropical cyclones. We average about 12 named storms in a year, 6 of which typically become hurricanes, and between 2 and 3 become major, which is a Saffir-Simpson scale of 3 or greater. So you can see here that basically tropical cyclones can affect Australia in the southern hemisphere. Notice in the Atlantic, there's almost no tropical cyclones that form. Only in the northern part of it. The southern hemisphere part of the Atlantic, this does not have them. And here's the season when they're here. They peak typically in September and then drop off after that, but you can still get a pretty good amount in October and even some into November, and there have some as late as Christmas time. And they begin to reform again by early as May. So where do they form? Well, beginning of the season, June, most of them form in the Caribbean or Gulf of Mexico. With time, we know it takes a while for the Atlantic to warm up. They begin to form further out in the Atlantics, and eventually, as waves begin to come off of Africa, they'll form further to the east and eventually reach their maximum in September when you get them both in the Gulf, Caribbean, and coming in from Mexico, from Africa here. Almost all hurricanes tropic is some form of tropical disturbance. Melissa had one that moved across, was an easterly wave, slowed down. When it slowed down is when it began to develop. Sometimes convective clusters can develop into hurricanes, but it's pretty small. Other times we get problems with the Saharan air layer. That's an air, think about a big giant dust storm. That is what the Saharan air layer is, literally off the Saharan desert. It moves towards the west over the Atlantic, particularly about 30 degrees north to 10 degrees north in that latitude range. And it's very dry air, very stable, very dusty. And when it hits a hurricane, a tropical cyclone of any type, it begins to weaken it, may actually dissipate it, or it can prevent it from forming. So these are always tracked as they're moving across. But when conditions come together, like they did with Melissa, you get lots of water vapor condensing. You're in a very humid air mass over the ocean. Lots of latent heat is released. Latent heat causes the air to continue to get heated, continue to rise. As it's rising up, it cools, more condensation, more latent heat. So eventually you keep getting hotter and hotter temperatures in the core, which help to cause it more instability. And when you get aloft, high pressure is up there now. You've got divergence in that area. So their life cycle typically starts with the depression, becomes a tropical storm at 39 mile an hour, and a hurricane at 74 mile an hour. Interestingly, hurricanes are typically very small. Melissa, literally from the eye out, had hurricane force winds of 25 miles. So if you were 25 miles from the storm, you were getting you were getting 75 mile an hour winds. If you were 1 or 2 miles from the eye, you were getting 185 mile an hour winds. So in literally 25 miles, you went from ridiculous wind speeds down to bad wind speeds, but not devastating. That's how tiny hurricanes are. They have major hazards associated with them. Most of the deaths occur either from storm surge or rainfall. And here you can see the chart. Rains. Why is there such amount of rain when the hurricane comes ashore? The hurricane formed over the middle of a tropical system. All it did for the days it was sitting out there was soak up the moisture. So that's what it does with all this moisture. It dumps it over the land when it comes in. Hurricane Harvey is the wettest one we've ever had, with 61 inches of rain over Texas. You can see here how it moved up, and it spent days over the Caribbean and over the Gulf of Mexico absorbing moisture. And when it finally came up to Houston area, it stalled. And when it stalled, it allowed all that moisture to just fall right over that area. And here is the extreme, ridiculous amounts of rainfall that averaged over Houston, Galveston area. Winds, they'll diminish rapidly once you come inland. In other words, if you live 75, 100 miles from the coast, your winds that you're going to get from that hurricane are going to be significantly less than if you lived right along the coast, right along the beach. So hurricanes are going to weaken for a couple of factors. One, they're getting away from the water, so you've lost your source of energy. So the hurricane itself, it begins to weaken. The second thing is oceans don't have a lot of friction. So once they hit land, the friction increases. You significantly slow the winds down in the lowest layer. What's a storm surge? Storm surge occurs because literally the hurricane is pushing water into the coast. So it's always going to be on the side where the winds are flowing into the coastline. So if they're moving away from the coastline, you're not going to get storm surge. But if they're coming towards the coastline, they're going to drive the water. The bigger the area of the strong winds and the stronger the winds, both influence how big that storm surge will be. So you can see here, the storm surge literally pushed the water up about 5 meters. High tide is 1 meter up normally in this location. So you wound up with 6 meters or 18 feet of water higher than normal sea level, all due to this particular hurricane. Then you can add some waves on top of that, maybe up to 5, 6 feet or 10 feet. All of a sudden, any houses, any structures that are near there just aren't going to make it. This was Mexico Beach in Florida after Hurricane Michael, which was a Category 5 hurricane, came ashore. Notice all the houses on this picture look pretty well organized and everything. Here is where it came ashore. Notice this is all due to storm surge. The storm surge literally covered this whole area, destroying all these homes. The biggest storm surge that we know of in history is 24 feet. Hurricane Katrina, storm surge was quite large. And Sandy, which you're going to tell me all about in a couple weeks, actually had 12.7 feet of storm surge. Be interesting to see why that occurred. Maybe you can tell me. And here are some of the other Saffir-Simpson wind scales of Category 5s. And you'll see Melissa was right in this area. The hurricane's intensity, literally stronger than Camille. So there's all kinds of challenges trying to figure out how hurricanes have developed through the years. We didn't have satellites. We didn't know what all was out over the tropics or anything. But we're getting better. We know that they're averaging, since 1995 to 2000, about 14, almost 15 hurricanes. Before that, from 1970, they're only down around 9. So you can actually see here how they jumped up. And interestingly, intensities have been jumping up too. And that's part of what global warming says would happen is not the number of hurricanes, but the intensity and the amount of moisture in the water will be able to do that. So I hope you got something out of this, and let me know if you have any questions.